Assalamu alaikum, Chem 30s. One of the things that we've always understood when we've applied Le Chatelier's principle to concentration changes is that if you add a stress or add some sort of substance that has essentially nothing to do with the system that we're testing, there is no shift in equilibrium. And in most cases, that is true. Now, what no shift in equilibrium actually looks like in the lab is, well, you add it to the substance and absolutely nothing happens. Now, if you add a substance to something else and something does happen, either a color change, gas produced, heat produced, a light produced, etc., a precipitate formed, then that means that there is a reaction which translates to that the equilibrium has been shifted. So before we rule anything out, remember that your powers of observation are stronger than the words that you write down on paper. So let's test out that hypothesis in the lab and see if what we say is actually true. So, contrary to what we previously held, if I feel the bottom of this is actually quite warm, so there's heat release, but there's also quite a lot of precipitate produced if you look over here. So there's definite signs of a chemical reaction, which is really signs that equilibrium has been shifted. Yet, copper chloride had nothing to do with the original system. Why did that happen? Well, let's take a look at the notes. So the system that we saw previously was the KOH to K plus and OH minus system. And this is, of course, solid, and these two would be aqueous. And this was in dynamic equilibrium. So, the usual rules would apply. If we added KCl, well, KCl breaks down into K plus and Cl minus. This is not a common ion, so it would have no effect. But this is a common ion. In fact, it's on the product side. So it'd be like we're adding products which would essentially favor reactants. Now, if we were to add NaCl, using the same method, since this is ionic, we could break it down into Na plus and Cl minus. Cl minus is not part of the reaction, so it would have no effect. And Na plus is also not part of the reaction, so this would have no shift in equilibrium. Now, what you would see with regards to this one over here is that there'd be no visible change or reaction. And that's what no shift means. Okay, is that there's no reaction that you would actually see in the lab. Now, here's the thing. When we added, and this was a little bit different, when we added copper to chloride, aqueous, and went against our intuition, which would be to write everything off that doesn't directly belong. So when we break this down, well, that goes into Cu2 plus, and that goes into Cl minus. Cl minus is not part of the system at all, and neither is copper 2 plus. Yet, we saw some sort of change or shift in equilibrium. And why is it that that occurred? Well, what we're going to do is, for this guy here, there came about a very important rule. And that is to check solubility first. When we look at the solubility chart and we look at the anion OH minus, we can see that the majority of substances that react with it are going to be slightly soluble or not soluble. The only ones that will be soluble is the ammonium ion, NH4+, and anything in group 1. But when we look for copper on the periodic table, we can see that copper is definitely not group 1. In fact, it's group 11. So copper 2+ forms an insoluble. Well, what that means is, so I'm going to just circle this and write forms insoluble compound. Okay, compound with 8 with OH minus. Now what that means is that, and I'm going to write this in a different color, OH minus get used up in order, and I'm just going to rewrite that a little bit better here, in order to make copper 2 hydroxide. And if we think back to Le Chatelier's principle, well, if this gets used up really just means that it decreases or gets removed. And so if it decreases, then the system will increase it back up. And so OH minus gets used in order to make copper hydroxide solid. This system then counters this by producing more OH. Whoops, I wrote 4, should be more. OH minus. So what this actually means, and we're going to write it therefore, the products are actually favored because they got used up. So then this brings us to a key rule here. And I know there's quite a few rules when it comes to this Le Chatelier's principle, but if you can remember them, you make your life a lot easier. The rule is, before ruling out that an entity, and we'll say an uncommon, it's specifically uncommon entity, so we'll write in brackets here, one that you can't find in the main equation, has no effect on equilibrium, always check solubility. Okay, and basically you can say it like this, and I'll write it in blue. Whatever side has the ion that forms an insoluble compound, so we'll just write an insoluble compound, is always the side that gets favored. And we'll just write favored here. So with reference to the example that we just did, we saw that the ion that formed the insoluble compound was on the product side, and as we see here, the products were favored. Okay, let's take a look at another system, because there's another instance where this occurs. So let's say, again, I could do the same system. Okay, so we're going to rewrite it over here. We'll just write a different alkali. We'll say NaOH, adding water to it gives you H plus and OH minus. Okay, so we have another example over here. And let's say I add HCl. Okay, now HCl is a strong acid, so that's going to break down at H plus and Cl minus. Cl minus is an uncommon ion here, and it doesn't form any insoluble compounds with any of these substances. Now, I miswrote this over here. Sorry, I just realized that. That's correct. It shouldn't be H plus and OH minus. It should be Na plus and OH minus. I'm not sure why I wrote H plus in the first place. So, Cl minus doesn't form an insoluble compound with any of these when we check the solubility table. And so we can cross that out as having no effect. Now, H plus is not going to form an insoluble compound with any of these here. Any of these entities. But remember from electrochemistry is that H plus and OH minus react to form water, right? We always combine the two when we were balancing our half reactions. So they always react to form H2O. And if that's the case, that means that OH minus is used up to make H2O. And used up is just another way to say decreased. And OH minus is a product, so if you decrease the product, well, the system is going to increase it right back up in order to counter that change according to Le Chatelier's principle. So, what this means is that products are favored. Okay, so we're always going to double check for common ions and for H pluses and OHs before we rule them out whether they form either a water or an insoluble compound. If they don't, then they have no effect in equilibrium. But if they do, then they're going to favor the side that has those ions that got used up.